Hello, and welcome to my first kind of progress update on the second computer that I've started in Starbound. I've already built one successful working computer. It was an 8-bit machine, posted about it before. This one is also an 8-bit machine, but it's supposed to be a stack-based architecture. It's considerably larger, and most importantly, my biggest goal building this one was to make it considerably faster. And the way I plan to do that is that while in the first computer it basically had serial output for every byte, this one has parallel output for every byte. That means that instead of sending 1 bit of information at a time, it sends about 8 bits. It sends exactly 8 bits of information at a time. So in theory, it should be about 8 times faster. I say in theory because the reality, based on the architecture thus far, is that it's probably going to be closer to maybe 3 times as fast, depending on how long it takes to execute certain instructions and what kinds of programs I try to run on it. But before we jump the gun, let me just kind of walk you through the computer, going basically just kind of from left to right, which is roughly in the order that I built things. It's not completely in the order, but I'll note that where it's not true. So what am I standing in right now with this huge panel of different wall switches? These are the human colony wall switches and all these AND gates and OR gates. This thing is the bootloader memory, right? And what it's supposed to do is just store all of the commands and information that I would like my computer to run as soon as it starts up. So right now it's not actually storing any commands. All I've written into it are a bunch of numbers. In fact, the integer is going from 0, which is this first row down here. All of this information is stored in binary, of course, because it's a computer. And then going to 1, and then 2, and then 3, and then 4, etc., etc. If you don't know how to count in binary, this is going to be a really confusing tutorial, or a really confusing walkthrough. I guess take a minute to read up on it if you really want to know. Or just enjoy the pretty lights and, I don't know, the mess of red wires that you're going to see over and over. Anywho, so it counts all the way up to 31, because we have 32 bytes, 32 bytes of bootloaded memory. It's extensible. I could build several more if I wanted to. It does take quite a while. Not as long as the RAM, but it does take quite a while. How does the bootloader memory actually work? Kind of a very quick and dirty rundown is this. The wall switches contain the information that I wish to actually send to the RAM, and then an input signal comes from the right via these OR switches over here, and that input signal selects which byte we wish to read. So right now you can see it's selecting this byte up here, and now it's moving to this byte up here. That signal is sent to all of these AND gates that you see on every row, and those AND gates have 2 inputs, right? One is that selection signal, and the other is whether the switch next to it, the switch to its left, is on or off. If it's on, then the AND signal sends on. If it's off, then the AND signal sends off. That output is then sent downward, right, to the output. And this output is ANDed with the signal that says should the bootloader be writing right now to the RAM. Currently it is on. And then that is sent over to the RAM input, where it is written to RAM. Sorry, that's a little bit confusing and fast, but this is going to be a substantially longer video if I walk you through the design of every single component. So where does it get the signal to tell it which byte to select? That comes from this thing that I'm standing in the middle of right now. This is the multiplexer, the RAM/bootloader's multiplexer for selecting which byte to look at. How does it work? Well, it receives an input down here. Right now, all of these OR gates are off, which means that currently 0 has been selected. So it has selected byte 0. And that signal is sent up to this kind of huge tree of AND gates, and this row of NOT gates here. If we turn on one of these, it will change our selection. And depending on which one we change, it will change our selection by a lot or a little. Okay, so the wiring is tough, but I'll just wire in a couple of switches here so we can watch this in action. So first, notice that right now, this AND gate here, right, whatever AND gate's in this column indicates which byte we have selected. Right now it's on the very bottom column, or the very bottom row, so we should say that it has selected the 0th byte. If I turn this on, right, now the input is 1, 0, 0, 0, 0, So it will select the first byte, which is the second from the bottom. Thank you, computer science. If I switch this here, then it will be the second byte, and if I switch them both on, it'll select byte 3, right? And then it'll go to byte 4. I've of course labeled all the rows because it's in hexadecimal, because it's intensely frustrating to try to remember what row you're on. And so on and so forth, right? If I continue to switch all of these, I could select as high as the 255th byte, or byte 255, which I guess is actually the 256th byte, because in computer science we start counting at 0. Anyway, so that's the crux of how the multiplexer works. The multiplexer is used both to select which RAM byte we want to look at, and also which bootloader byte we wish to load from. You might notice that every 16 bytes worth of bootloader or RAM, there are these kind of interstitial rows whose only purpose is actually to be kind of a waypoint for signals. I don't know why, but between now and when I built my last computer, there has been some change in wiring, such that you can no longer send a wire an arbitrary distance, it appears. Now there seems to be a maximum distance that a wire can carry a signal. If you try to carry your wire too far, it'll just disappear on you, which is frustrating. But the way that I got around it was that I made these points where the signal, goes to some OR gates that are just kind of dummy gates to send to renew that signal and send it another 16 bytes up. Okay, so we should take a look at the RAM, which is sitting next door, right? This RAM tower, this is 64 bytes of RAM. You might have noticed we have only 32 bytes of bootloader and 64 bytes of RAM. The RAM is larger because you want lots of working memory. RAM is quite important. If you don't have enough RAM, you can't run certain kinds of programs. The bootloader is only the instructions, right? And RAM is not just for instructions, but also for data that you just want to store, or possibly if later I end up hooking up certain bytes of the RAM into input or output devices, we'll need more RAM for that too. Anyway, how does the RAM work? Once you get a signal from the multiplexer to tell you which byte you wish to load, what the RAM will do is it will take that and also a signal that indicates whether you wish to write the RAM or read from the RAM, and combine that into some AND gates and send those to these latches, which actually store whatever information is supposed to be in RAM. And then that signal gets sent out to the output or taken in from the input. So what do we have here? The output goes to this top row, and the input comes from this bottom row. I know that's a little bit confusing looking, but trust me, it was the easiest way to make the wiring not intensely frustrating. You'll notice that the RAM is very densely packed. There's almost no free space between any of the gates here, and that's because there's a lot of RAM. And if I put any more free space in between it, the RAM tower would just get bigger and bigger and bigger. And I'll explain later why that's even more of a problem than it seems to be. Anyway, the RAM's job is just to store all of the information that the computer is using right now. And ordinarily, I would tell you, certainly if I were working on my previous computer, on the previous version of Starbound, I would tell you that when a latch is on, it indicates that that latch is currently storing a 1, and when it's off, it's storing a 0. But that no longer appears to be the case. For some reason, some latches do not do what they're supposed to do. I've noticed that some latches will send an off signal while they're off, as these two appear to be doing, and some latches will send an on signal when they're on, as this one appears to be doing. But sometimes that's not true. I've found that sometimes an off latch will actually send an on signal, which is intensely frustrating for debugging things. Let's see if I can find one and show you what I mean. Let me just put a dummy OR gate here, right? And if I wire the input of that OR gate to a latch that's supposed to be on, it will give me an on signal. If I wire it to one that's off, it will give me an off signal. Okay, alright, this one seems to be working, giving me an off signal. Good. And what if I send it to this one over here? Oh, very curious. I've just wired it to this latch here, and this latch you can see is displaying off, but it's sending the signal on. Starbound devs, please fix this problem. It's making it very hard to continue building this computer, and building computers is already kind of hard, so now it's super hard. Please fix it. Anyway, alright, so that's the RAM. And the RAM is, again, the working memory of the computer. It's how it does most of its calculations. Let's move into our next section. Over here, now we've got another kind of memory. What I'm standing in the middle of right now is the data stack. So I mentioned earlier that this is a stack-based machine. What that means is that the CPU doesn't have several discrete registers. It really only has two kind of stack registers: the data stack register and the return stack register. And there are a couple other really specialized ones, but the idea is that data stacks and stacks in general make CPU design a lot easier. My last one was kind of a lot of frustration in deciding what registers should wire where and exactly how many I needed and all that kind of stuff. What the data stack is it implements a stack, right? Like the same kind you would talk about in software, or to use a really common analogy, a stack like a stack of papers, right? You store a lot of information, but only whatever is on top of the stack is easily accessed. That analogy is a little unfortunate because the stack is built the other way, so that the top of the stack is actually at the bottom, and I can build it higher, and whatever's the topmost entry will be the bottom of the stack. Sorry about that, I just didn't want to dig downward. Anyway, so what does it do and how does it do it? Basically, its whole job is that if you tell it to start accepting data, it will push information into that data, to that stack. Let's see, do I remember which one was push and which one was pop? I guess we'll find out. I think this is push, right? So right now what it should be doing is it should be taking this input over here. Oh, whoops, that was pop, my bad. No, it's push, okay. It should be taking the data input and sending it up these latches. Unfortunately, the latches do not display whether they're on or not correctly, which again makes this very frustrating. But every tick, right, whatever information is taken from the inputs, which are down here, is pushed up one row, and every tick while it's in pop mode, that information is pushed down one row. Again, it's really hard to show you exactly how this is going on, or even to really explain it to myself, because the latch gates don't always show what they're supposed to be doing. So right now it's popping, so these signals should be traveling downward. Indeed they are. I have no idea why latches occasionally decide to work and occasionally decide not to. Again, intensely frustrating. But pop sends data downward and push sends data upward. This over here, this is the top of stack register. It's not really implemented totally yet. It's not connected to anything other than itself. But its goal will be to just let me access the top two elements of the stack, which is a really useful thing for stack architectures. Over here you have another stack. This one's the return stack instead of the data stack. The only real difference between the data stack and the return stack is that the return stack is mostly meant for storing addresses and RAM, whereas the data stack is meant for storing like numbers that you want to do operations on. They are structurally, like in terms of hardware, almost identical. The only difference is that the return stack is not going to get a top of stack register. How do they work? Real quick. It's basically a shift register. It's actually 8 shift registers that can be shifted upward or downward, depending on whether I'm trying to pop or push data from the stack. Whether it's popping or pushing is managed by these AND gates. They get a signal from either the pop input or the push input to decide which one to do. Other than that, it needs the clock signal, which is, by the way, this flashing OR gate is receiving a clock signal. The actual clock is right over here. The clock signal is sent throughout the machine just to make sure all of the components are staying in rhythm. All it really does is it takes one of the standard Starbound clock elements and through kind of clever use of a NOT gate, an AND gate, and the propagation delay between gates, makes sure that the output is always just kind of a very brief blip of onness. So you see the AND gate is only ever on very momentarily, and that is one tick by this computer's measurement. Let's keep going. Over here is the arithmetic logic unit. The arithmetic logic unit, I think this is one of the biggest improvements that I've made since my last computer, because my last computer didn't really have an ALU, it just had a bit adder. The ALU in this version is a little more complicated. There is still a bit adder. This section up here, this is a bit adder. What it does is it takes inputs from this row of 1 byte and this row of 1 byte, adds the results and sends them to this byte. You can see that they're both off right now, which means that the input is 0 plus 0, and the output is 0, because 0 plus 0 is 0. We can change that really easily. If I give some inputs to what we have, right? So if I try to get it to add, let's say 3 and 2, which I can do like this. So I'll represent 3 on the bottom row and 2 on the top row. If it adds 3 and 2, we should get, what, 5, right? So here's, 5, right? This bit is worth 1, this bit is worth 2, but it's off, this one is worth 4, but it's on, so 4 plus 1 is 5, right? That's the bit adder. Again, one of those topics you can look up on Wikipedia if you're really curious about it, but suffice to say I've implemented it using this mess of OR gates and AND gates, and XOR gates and AND gates, I should say. What does the rest of the ALU do? The rest of the arithmetic logic unit's point is to decide which command we're trying to execute, and then to execute it as in terms of anything that has to be calculated, right? The inputs all come from here. So here's 1 row of input, here's 2 row of input, which means that the arithmetic logic unit can take as many as 2 operands, right? Again, I will demonstrate. I'll just turn on, say, 2 of the bits here. So here's the input to one of them, here's the input to the other. I'll just turn those both on. So the first input's going to be 2, and the second one's going to be 4. So 2 and 4, right? And then over here, these bits are inputs to decide which command we want to run. If I turn on all 4 of them, that executes command 15, right? And command 15 happens to be addition. So the output of the ALU over here is going to be 2 plus 4, which is in fact 6, right? And if I run back and I select a different command, I can also select subtraction, right? Which will try to subtract one from the other. That one's going to be a little bit weird. It's like trying to subtract 4 from 2, and it'll give me this this rollover value, as if we had a 1 over here from which we were borrowing. I can get into the specifics of how that works, but the quick and dirty version of it is that the subtraction algorithm works the same as the add algorithm, except it takes the 2's complement of one of the inputs, and then adds them, and then takes the 2's complement of the output. Again, kind of a long and boring computer science lecture, not what you're here to see. But I can select up to any of 16 different commands for the ALU. Real quick, some of them are. So you've already seen add, you've seen subtract. There's also increment and decrement, right? Those are just to increase or decrease one of the operands by 1. And those are selected up here. I have a whole bunch of unused commands here. This is a multiplexer again, but everything over here is unused because I just haven't implemented some of the commands because I haven't decided what they should be yet. Right now I've implemented all the commands that I definitely know I want my machine to have. The first 6 commands are all bitwise operators. The first one does exclusive OR, right? So if I select the exclusive OR operator, the output will be 0 because there are no bytes in common. Let me go ahead and do that. Let's see, yeah. No, it should be selected right now. Oh, so it is. Oh wait, what am I saying? Shouldn't be 0. It should be 6 because the exclusive OR of 4 and 2 is just all of the bits where exactly one of them was on. So it'll give us 6. Okay, so had a little panic attack, thought it wasn't working, totally was working. Next up, there's the OR, which will actually give us the same output. It's kind of boring. OR just isn't exclusive about it. I guess that's kind of tautological. Well, whatever. There's the input for AND gates, where it will just give us the and then there's also the NOT gate, which will give us the inverse of one of the operands. There's the upshift and downshifts. Those will just move the bits of one operand one to the left or one to the right. The outputs of each of these commands is sent over here and then directed downward to the output. Again, it's kind of a hot mess of red wire, but it does work, and I've tested all of them. Moving on from the arithmetic logic unit, we have the memory address register and the program counter register. Right now, these aren't used for anything, but I can tell you what they will be used for. The memory address register is supposed to tell you which byte in RAM we are currently trying to read or write from. And the program counter is supposed to tell us which byte in RAM corresponds to the instruction that we are currently trying to execute, or that we are next trying to execute. Again, right now they're not really hooked up to anything, so there's not much to talk about with those. Over here is the last thing that I've built so far. You'll notice that the CPU is conspicuously missing. I have not built the CPU yet, or at least not much of it. I guess technically the ALU, depending on who you ask, is part of the CPU. The CPU's biggest job is to decide what things should be inputs and what things should be outputs, at what times, based on what instruction we currently have loaded. All of that is going to take a while to implement. It's the most complicated part of the machine by far, even though it's not necessarily the largest. Definitely the largest goes to RAM. What is this structure right here? This is the bootloader operator. So let me just turn this on, and I'll kind of explain it while it runs. So when I flip that switch, and it's a momentary switch, so I can turn it off right again. What it'll do is it'll start incrementing this register up here. So this register, that's odd. It's not supposed to be doing that. Why is it doing that? What's going on here? Oh, I know what it is. I left the ALU switches on. Ah, how silly of me. I have to go turn those off. Yeah, these are not a permanent part of the design, and if I leave these in, it will cause all kinds of problems. Sorry about that. Alright, let me get back to what I was doing. Alright, so, as I was saying, the way that's supposed to work, the way the bootloader is supposed to work is that it uses the ALU to increment this register, right? So it's counting up one at a time, right? So right now it's on what? We've got 1 plus 2 is 3, plus 8 plus 16, so what, 27 right now. Now it just moved on to 28, right? And it keeps adding 1 to the register, and basically all this is doing is sending this signal all the way back to the boot memory and to the RAM, and selecting which byte in that in both of those we are trying to load at that given time. What I mean by that is that it's telling the bootloader, okay, now it is time to send byte 1 of the pre-programmed boot memory to the RAM, and now it's time to send byte 2, and now it's time to send byte 3, and it'll do that, one hopes, until all of the bootloader's memory has been loaded into RAM, and the computer is ready to just run whatever we've pre-programmed into the bootloader. You see it right now, it is just reset to 0. The reason it did that is that it got to the end of the bootloader memory, right? It's programmed to stop as soon as it gets to 32 bytes of RAM. It actually goes a little bit past that just because it was easier to implement. But once it gets to 32 bytes of RAM, it is officially done. The entire bootloader memory has been inputted. If I make more bootloader memory, I can easily change it to do 64 bytes or 128 bytes or whatever it is I need. All of that output is sent down to these gates over here. It also sends a signal while it's running that says, hey boot, please, hey bootloader, please send your information over to the RAM. The problem is, and this is where I'm going to get into the big crippling errors in Starbound logic gates that are preventing my project from going forward right now, or at least slowing my advancement, is that the signal gets a little bit corrupted along the way. So right now, this is just a flat copy of that register. Again, I have a lot of these relay OR gates, right, that are just there to kind of carry the signal past the maximum wiring distance. And you can see that it is slowly incrementing, right? It's sending that signal over. And if we follow this signal, right, okay, so here we are at 7, oh, and we just moved to 8, and that signal should keep on going, and keep on incrementing. There it's at 9. So far things are going well. It should count up to 10 next. So far so good. Counts up to 12. Do you see that flicker? That's my biggest problem, right? For some reason, if you get far enough away, it stops working, right? Even though when we were just over there, we witnessed it count all the way up and reset with no problem. If you get far enough away, information from faraway gates starts to flicker, and that causes me all kinds of frustrating trouble. So it is counting upward, right? But it spends a lot of time not displaying what it's supposed to be displaying, like kind of taking a moment to try and decide what the value actually is. And you can see that this means that the multiplexer is kind of slowly trying to select the next byte up, but every time it does that, it just kind of freaks out for a while it tries to remember what signal came from all the way over on the right. Now, I'm not 100% sure why this happens, but if I had to guess, not being one of the developers for Starbound myself, I would guess that they probably have some means by which the game tries to load only the blocks that are nearest to the player, and since now my avatar is sufficiently far enough away from the bootloader counter, it's no longer really loading the bootloader counter correctly, or something like that. I don't know, like I said, I'm not a dev, so I don't actually know. But this problem is intensely frustrating. It means that everything that I send to the RAM is not properly getting sent to the RAM, and the only way that I can think of to solve this problem is to tear down a lot of the stuff I've built way over to the right and bring it all the way back to the left and try and just build it closer, or I guess maybe somewhere down here underground, so that it will not degrade the signal as it continues. I didn't used to encounter this problem. On my first computer, I did not have this issue at all. And now that I am having it, it's, again, intensely frustrating. So devs, if you're watching this, please, please, please fix this problem. It would make my life way easier. Of course, if you don't wish to cater to the specific needs of exactly one of your user base with a really esoteric interest in your game, then I understand where you're coming from, and maybe I should just, I don't know, break out some kind of more reasonable software for developing computers. But anywho, so that's the basic tour of the computer so far, and I hopefully will be able to update you with more progress later. Maybe I will find some way within game to solve this problem. If not, I don't know, maybe I'll look into maybe modding or something to help make this easier to do without all of these frustrating glitches. Other than that, thanks for watching. I know it was kind of a long lecture, but hopefully I will have a much more exciting update soon. Right, see you later.